Hello everyone, this is Lucas Ellett. Today I'm going to go over the method of sections. This is going to be covering your second exam, and here is the problem that we're given. So you can see these are the forces, this is the structure that we're given, and here's the pin support, the roller support distances, and it's asking us to find the forces and members EG and ED right there. So our first step is to determine if it is statically determinate. Use this formula. 2 times the number of joints should be equal to the number of members plus the reactions. You've got 11 joints, and remember that each letter represents a joint. So there's 11 letters. And there's 19 members. So when you have 2 letters and a line connecting, that's a member. And 3 reactions. So there's going to be 1 vertical reaction here, and a vertical and a horizontal at this pin support. So it is statically determinate because they equal each other. And the next step is to draw the free body diagram. So I know this may look a little bit hectic, but basically what I did is I drew everything, but I replaced these supports with my assumption of what the reactions are going to do. So I assume that the vertical reactions are going up and the horizontal reaction is going to the right. There's also a side note here for the section lines that you also will draw. To find EG and DE, that a section line cannot pass through more than 3 members. So for this problem, you're going to need 2 section lines. What that's going to do in the problem is that you're just going to need to draw each section independent of each other, so they won't affect each other. You'll just need to, for section 1 for ED, either take the left side or the right side. But before I get into that, I'm going to quickly go through these reactions, because for method of sections and for method of joints, you're going to need to calculate the reactions. Again, I'm just going to quickly go through it because I already made a video on reactions. So if this is confusing, please go back and watch that video because it's probably more in-depth than what I'm going to do right now. So for the reactions, I like to start with using moment, and I'll use moment twice at each support. So I'll use a moment at J, which will give us RBV, and then I'll use a moment at B, which will give us RJV. So I started here at J, taking the moment, and this is what I got. So what will happen is this 50 kips, since it passes through J, it's 0, because its perpendicular distance is 0. And this RBH passes through J, so its perpendicular distance is 0. And all you're left with is RBV, this 50 kips, and this 30 kips. You're only going to have three things to calculate there. And this RBV is negative because it rotates this way about J. And the other two, this 30 kips is positive, this 50 kips is positive. And of course, they're perpendicular distances. So, for example, 30 kips is going to have a distance of 9. And you'll just calculate that out. I got RBV is a positive 43.125 kips in the upward direction. This is what I got for RJV. Again, I'm just going through this quickly. This is just showing the calculations for the reactions that I got, so we can dive into method of sections, because you will need these reactions to use method of sections. Okay, so now we can go into the method of sections, and I'm starting with the first section line that I made to find ED. And what you're going to do is you're going to either take the left side, which I did in this problem, or you're going to take the right side. Either way, as long as you follow the correct process and think through it, the similar way, you'll get the right answer either way you do it. So you can take either side. Just take whatever side looks less complicated. So in this case, I took the left side. And I rewrote it here, and you can see where I drew the section line is where you're going to draw your members like so. So I'm assuming that they're in tension, so I'm drawing them away from the joint with arrows of where they would be going. These are the three formulas that we have at our disposal to find ED. And a way to think through it is you're going to use whatever formula gets rid of the other two unknowns. So the other two unknowns are DF and EC, and we want to pick a formula that will not include them, basically. So the problem with f of x is that all three would be included, and we can't find three unknowns in one equation. We couldn't take moment, because if we do moment about d, it will cancel out our ed. So we have to use f of y, and that's good because it has a vertical component, and the other two don't. So these two will not be included in our equation, and edy will be. So I wrote that down here. And for edy, you're going to need this angle that it goes at to find the y component. So this is the formula right here to find this angle. It's going to be tangent theta x is equal to rise over run. So it rises 9 feet. ED rises 9 feet, and it runs 12 feet right here. So it's going to be tangent inverse 9 over 12. So theta x is 36.87 degrees. F of y, you're going to use this formula. This means that everything going up is positive, and you're taking the summation of the forces in the y direction. So we have the 43.125 kips, which is a reaction that we calculated. You're going to have edy, and you're going to have a negative 50 kips. It's negative because it's moving downwards. And that's all going to be set to equals to 0. You add these two together, you get a negative 6.875 kips plus ED times the sine of 36.87. So if you use SOHCAHTOA with this angle to find the y component, you'll find that it's sine of that angle that you need. And then you'll move that to the other side, which will become positive 6.875, and divide by sine of 36.87. And since our answer was positive, it's in tension. Because this is given right here, that if we get a positive answer, it's going to be in tension, and that means it's moving away from the joint. And if it's compression, it's negative, and it's compressing the joint. So this answer was positive. That means ED is moving away. So that's right. Moving on to section 2. So I chose the right side because it looked a little bit simpler, and I didn't want to repeat what I did up here. So in this version, I chose the right side, which is going to be everything over here. And this is going to find us EG. So you can see I drew everything as it is, except until it hits this section line. And I'm assuming that everything again is in tension. So it's all moving away. But this time EG is on the top. And we can't use f of x because that would give us 2 more unknowns. And we can't use f of y because it doesn't go in the y direction. So we can use the moment. And if we take the moment about f, So basically what I did here is I extended, because these will connect to f. So if you take the moment about f, it will cancel both of these unknowns out, and all you're left with is EG. This is what your moment will look like. So I can get it all in here. So you're going to have EG, and its perpendicular distance is 9. Then you're going to add this 30 kips. It rotates this way, so it's positive. Its perpendicular distance is 9. You're going to have this 50 kips, and it rotates this way, so it's negative, times 24. 12 plus 12 is 24. And then this reaction is going upwards. 56.875 kips rotates this way. So that's positive, times 24 feet is all equal to 0. Then from here, you use algebra. So you're going to get this 9 feet times EG. All of this right here is 435 kip feet. That's kip times foot. You're going to move this to the other side. So it's going to be a negative 435. Divide this 9 feet over. Feet cancel out. And you're left with EG is equal to a negative 48.3 kips. And remember, when we get a negative answer, that means it's in compression. So I rewrote it here as a positive, but it's in compression. So that's important to note. It's still in compression. And I rewrote what joint G would look like. Since our assumption here was incorrect, that it is compressing joint G. So I wrote here, you can see it compresses joint G. I also realized that my previous explanation of ED times sine was a little bit bare bones. So I'm going to take an extra second and explain why I use sine here instead of cosine or tangent or something else. So we're looking for the y component of EDY right here. And we already found theta x is 36.87. So I'm going to redraw this into a triangle. This is what ED, the components of ED look like. The x component and the y component. You're going to have this x component. You're going to have the y component. There's the angle we found. And we need to find this y component. So we need one of these three formulas that will give us the y component and EDY. And the one that gives us that is sine. So you look at the perspective of the angle and you say, okay, I need the opposite and the hypotenuse in one equation. The only one that does that is sine. So this is what it's going to look like. EDY is equal to ED times the sine of your angle. Okay? And again, you use sine because it includes the opposite and the hypotenuse. That's why. And that will complete method of sections.